Okay, so we are going to now learn about a more rigorous way of solving problems in elasticity, both two-dimensional and three-dimensional elasticity. And what we are going to do in this part of the course is try to solve some very key problems which may look unrealistic at first glance, but they are very key problems that can be used to build solutions to more complicated and more realistic problems. So that's our purpose. We'll do both 2D and 3D problems. But before that, let us understand the method that we are going to use. Uh, we are going to use something called Fourier transforms, actually something called continuous Fourier transforms. And I understand that you have some introduction to Fourier transforms already. You might have done one-dimensional Fourier transform. So we are going to take this to two and three-dimensional Fourier transforms. The idea is if you understand Fourier transforms in one dimension, the ideas in two and three dimensions are not very difficult to understand. So I'll just take you through quickly the basic concept. So the way we are going to define Fourier transform of a function. So we have a function fx for which we define a Fourier transform. So what Fourier transform does is it changes the domain of the function. So it takes it from domain x, which is from minus infinity to infinity, to a different Fourier variable zeta. And this is what this integral is used to take this from x to zeta. So we multiply the function by e to the power minus I zeta x, integrate from minus infinity to infinity, and then we get transform this function from a domain of x to that, from a function of x to that of zeta. So in many books, um, let me first explain the inverse Fourier transform. So if you now have the f bar zeta, which is the Fourier transform of fx, then you can get fx back by doing an inverse Fourier transform, which we denote by f inverse, and that is defined as 1 by 2 pi, again integration from minus infinity to infinity. So this is the Fourier transform that you had. Multiply that by plus e to the power I zeta x, integrate over d zeta, and you get a function of x back. So this is the Fourier transform, this is the Fourier transform, and this is the inverse Fourier transform. They together form a pair, and this inversion process and the forward process is possible, provided that this integral, that the modulus of the function integrated from minus infinity to infinity is not divergent. It doesn't go to infinity. So if this integral does not go to infinity, these two integrals form respectively the forward Fourier transform and the backward Fourier transform. Now, in many books, slightly different definitions are used. So, for example, we have used the minus in the forward Fourier transform. Many books use e to the power I zeta x for the forward Fourier transform, and then use e to the power minus I zeta x for the inverse Fourier transform. And this factor of 1 by 2 pi, many people use 1 by root 2 pi here and 1 by root 2 pi here. That's also a valid definition. So you have to basically define the Fourier transform and its inverse correctly, so that f of f inverse of a function gives the function itself. So once you do that, you should stick to that definition for all the further derivations that you do. So we are going to stick to this definition. So the minus in the inverse Fourier transform, and the plus in the the minus in the forward Fourier transform, and plus in the inverse Fourier transform. That's what we are going to do. And 1 by 2 pi for the, in the formula for the inverse, nothing, 1 for the formula of the forward Fourier transform. Now, there are certain rules, certain relations that the Fourier transforms follow, which is quite easy to prove. So let us try to do some of that. So, for example, uh, if we want to do Fourier transform of fx minus a, you might have learned about this. This is called the shift theorem. So what you do is minus infinity to infinity. So Fourier transform of fx minus a is equal to minus infinity fx minus a e to the power minus I zeta x dx. So now take x minus a equal to u, so dx is equal to du. Both go from minus infinity to infinity, so this remains as fu e to the power minus I zeta u and e to the power minus I zeta a du. This is a constant as far as this integral is concerned, so it comes out of the integral and you have Fourier transform of f. Okay. Fourier transform of fx, the symbol that we use, this is a function of zeta, but we don't often don't write the zeta for the when we use this notation, we don't write the zeta. Sometimes for this we will use the notation f bar zeta, and then we will write the zeta explicitly. Okay, so this is one. This is called the shift theorem. There's another one which is f of d dx of fx, and that would be equal to this would be the Fourier transform of d dx of fx. And now you can choose your integration by parts. So if you use integration by parts, what you get is minus and then this. So this goes to 0. This has to go to 0 because of this, and because this is the theorem that we used, that this is bounded. This integrated from minus infinity to infinity should give you a finite number. In that case, this has to go to 0 at both the infinities, plus infinity as well as minus infinity. So this leads to I zeta f bar zeta. So this is what it will lead to. Right. So this is the differentiation theorem. This is the differentiation theorem, and another important theorem that we are going to use is the convolution theorem. So convolution of two functions, you might already know, we denote it like this: two functions of let me write explicitly. So this is the convolution symbol, and this is equal to convolution is also commutative. So f convoluted with g is same as g convoluted with f. You can easily show that by a change of variables. Now a Fourier transform of a convolution would be a double integral. Would be this times e to the power minus I zeta x dx. So now you can take again x, you can x equal to let's say x minus, or do this. So let's write the x as, let's do it right here. Let's write the x as x minus a plus a dx. Okay, now take this f a, this is a function of a, take this function of a e to the power minus I zeta a from here, and then this dA into 1, and then we have another one which is gx minus a e to the power minus x minus a to dx. So is uh, this is same as gu. If you replace x minus a by u, this is, if you replace this by u, this becomes u, this becomes u, and this becomes du. So if you replace x minus a by u, and then you are left with this. This also is the Fourier transform of A. So what this leads to is Fourier transform of F times Fourier transform of G. So the convolution theorem states that the convolution, Fourier transform for convolution, is the product of the Fourier transform. So this is the convolution theorem. So these are the three theorems that we are going to find very handy. I have proved them in the 1D case, so we will extend them to multi-dimensional cases soon. Okay, now, so these are the theorems that we have learned, and then extend it to say 2 dimensions. So when you extend it to 2 dimensions, what we do is we take two Fourier transforms. So first we take a Fourier transform with respect to, let's say, x1. So one Fourier variable is zeta 1. We take a Fourier transform with respect to x1. That means we multiply the function by e to the power I zeta 1 x1 and integrate over x1 to get a function of zeta 1 and x2. So x2 remains, x2 we are not integrating over. Then you do a Fourier transform over another Fourier variable zeta 2 and x2. So finally you get a function of zeta 1 and zeta 2. So the formula is, it's just a sequential application of e to the power minus I zeta I xi to the first variable and then the second variable. So the final integral becomes, this is a function of two variables x1 and x2. You are multiplying it by zeta 1 x1 and zeta 2 x2, integrating from dx1 dx2, and doing this double integral to get a Fourier transform function, which is a function of zeta 1 and zeta 2. Now you will notice that this guy can be written as zeta dot x, where zeta is a vector having components zeta 1 and zeta 2. These are the Fourier variables, and then x is another vector x1 x2 as its component. So extending this to multi-dimensions is easy. So if you have a function of x where x can be x1 x2 x3 maybe, you multiply it by exponential of minus I zeta dot x and integrate over dx1 dx2 dx3, you get the Fourier transform of fx. To do the inverse, you want to get fx, you know the Fourier transform f bar x, so f bar x exponential I zeta dot x, and this is the factor that we are going to use. This is going to be 1 by 2 pi square in case of 2D. It is going to be 1 by 2 pi cube in case of 3D. So this is, D is equal to the dimension of space. So it will be 1, 2, and 3 in case of 1D, 2D, and 3D. And you can easily see that the 1D expressions are returned when D is equal to 1. Now, the other thing that I want you to notice, we will most of the time omit these long list of integral symbols. So even for multiple valued functions, we are going to just write this, and this will mean, according to the context, it will mean 1, 2, or 3 integrals, as the case may be. Okay, so this is the general form applicable to d dimensions, and this general Fourier transform also is going to obey almost all the rules that we proved for the one-dimensional integral. It is going to obey the shift rule, which is what we had proved. So if you want to now prove the shift rule, so let's say do it for 2D. So what you have to do is f x1 x2 e to the power minus I is your f bar zeta in 2D. And for the shift, uh, so let's write it for any dimensions. Let's erase this. So this is the your generalized Fourier transform of any a function of any number of variables. So now if you define a new function in terms of fx minus a, then f x minus a e to the power minus I zeta x dx is the Fourier transform of fx minus a, where obviously a is a constant vector which is of the same size as x. So for 1D it's just a scalar, for 2D it's a two-dimensional vector, and the three-dimensional vector in 3D. So now you can do the same thing exactly as we did for the one-dimensional integral. X minus a is equal to u is another vector, so dx would be equal to du, and the result follows. You can try it out yourself. The same the other important theorem is the derivative. So if you want to find Fourier transform of del x k of f of x, say, then what you are going to do is you're going to do this. So this is what you're going to do. Now, to prove this, we will have to determine this, we will have to apply the divergence theorem. So with the divergence theorem, we write this can be written as del xk of fx e to the power minus I so this is the first term, and minus fx del xk of e to the power I minus I zeta dot x and the whole thing dx. So this is the first application. We have not applied the divergence theorem yet. Only thing that we have done is this whole expression, we have written it as a complete derivative minus some term. So this is the way we do integration by parts in multiple dimensions. So now if you look at it, this is amenable to the divergence theorem. So this would turn out to be fx e to the power minus nk at at delta v, where delta v is at infinity, because this domain is an infinite domain. You are actually integrating, you're doing a three-dimensional integral from minus infinity to infinity. So this domain is at infinity, and we have assumed that this function goes to 0 at infinity. So this is going to be 0. So the surface term that comes from this quantity is going to be 0. And now del xk of this will simply be, and this is important, this is an important result, del xk of e to the power minus I zeta dot x is same as del xk of e to the power minus I zeta m xm, which is e to the power minus I zeta m xm times I zeta m delta mk. So this is what it is. So this part will become minus I. So this part will become plus I zeta k f bar zeta. So you can easily prove that this is the case provided fx goes to 0 at the boundaries at infinity, at the boundaries at infinity. So so we have the result that f of so this is the derivative theorem. The convolution can be proved very easily. Now convolution for 2D functions, for example, or even for 3D functions, the convolution of f and g is defined as fx minus a into g a dA. This is how it is defined in 3D. And you can easily prove that the three-dimensional Fourier transform of f g is three-dimensional Fourier transform of f times three-dimensional Fourier transform of g. This is your convolution theorem in any dimensions. So in all the dimensions 1, 2, and 3, these three results are valid. Only thing that you have to remember is when we apply the differentiation theorem, we are taking a derivative with respect to the kth variable. In case of multiple dimensions, we are taking a derivative with respect to the only variable, that is x, in case of single dimension. So here we get the kth Fourier variable when we take a derivative with respect to k. In case of 1D, we take derivative with respect to x, so we get the only Fourier variable. We get I zeta. Here you will get I zeta k. If you take if you take the derivative 2 times, you can show that if you take, say, kl, you can show that you will get I zeta k times I zeta l. That's also easy to show. So this is a relation that we are going to use a lot. This is also a relation we are going to use a lot. So it makes sense to remember them. Okay. So yeah. So these are the results that we are going to use, and this is, I have written this for 2D, for 3D also it holds. exactly as it is. Okay, so let me stop here for the time being. We will derive a few three-dimensional and two-dimensional Fourier transform pairs in the next class. And we are going to use those. We are going to build, because this is not available as it is in any book. So we have to derive our own relations, keep them together in one place so that we can use them to quickly solve some problems. The pain is worth it, because as you will see that there are many classes of problems that, if you understand this language of Fourier transforms, becomes extremely easy to solve, extremely easy and straightforward to solve, at least up to some extent. uh, let's see that in the next class.